Okay, welcome back everyone to this tutorial series and specifically um, this set of slides on mathematical preliminaries. So now that we've talked about uh, the sort of basic definitions of what's a set, what's a subset, cardinality, power set, empty set, and universal set, I want to talk about operations that can actually be done on sets. And so the first one I want to talk about is the set union. So if we have two sets, A, A and B, then the union of these two sets, the union of A and B, is defined as the set of elements X such that X is in A or X is in B, right? So let's look at an example. If I have the set A, 1, 2, 3, and the set B, 2, 3, 4, then what is A union B? Well, it's any element X in A, so any element 1, 2, 3. This is all the elements in A, and then any element in B, so 2, 3, 4, right? These are the elements in B. But because sets contain distinct non-repeating elements, what I can do is I can say, oh, well, this second iteration or repetition of 2 and 3, I can just delete. And so my set union becomes 1, 2, 3, 4. Next question, which is actually a nice, interesting question. If U is the universal set and S is some other set, let's specifically say that it's in the context of U, then what is the union of the universal set and that set S? Well, we're actually seeing the result of a more general property that if you have a set A, which is a subset of a set B, then A union B is just going to be B, right? So why? So I can illustrate this with a Venn diagram, right? So if I have my set B on the outside and my set A on the inside, then the union of my sets B and A is just going to be everything in here, right? But this is actually B, right? And so, in particular, if we go back to this initial example of taking the universal set and doing the union with some set S, because that set is necessarily a subset of U, then this is going to be the universal set. So let me put an extra 2 bars on top of the U just so that we don't confuse the set union operation with the universal set. Okay, the next set operation that I'd like to talk about is the intersection. So in the intersection, suppose you have two sets A and B, then the intersection of these two sets, so A intersect B, is the set of elements X such that X is in A and X is in B. So for X to be in the intersection, right? So we always draw this classic Venn diagram when talking about set intersections. So if this is my set A, this is my set B, then the set intersection is, whoops, can I go back? Yes. The set intersection is just the guys in the middle, right? So these guys here, X, are in A and they're in B, right? So for instance here in example 1, if I have a set A, 1, 2, 3, and a set B, 2, 3, 5, 6, then the intersection of A intersect B is all of those elements such that they belong to A and B. So 1 is in A, but it's not in B, so that's no good. 2 is in A and it's in B, so that's good. 3 is in A and it's in B, so that's still good. Then 5 and 6 we can see just belong to B, so I can actually close my set there. Okay, so if I take the next example here is if I take, let's say, an empty set, and actually here it says the universal set, but just let's take any set A, right? Then what's going to be the intersection? Well, what we're trying to define here, we're trying to say that this is going to be the set X such that X is in the empty set and X is in A. However, there is no element, by definition of the empty set, there is no element X in the empty set. And so imagine doing some kind of like double for loop search, right? So if you do something like for X in the empty set, for X, let's say for, let's say Y. Well, yeah, so you don't even need a double for loop actually. So let's say for X in A, right? If X in the empty set, right, then concat X to A intersect the empty set, right? I mean, if you wanted to do this properly, you would have to have like two for loops, two blocks of for loops, because you might be missing elements that are just in the other set. But for our purposes here, just for this illustration, if I'm going over this for loop, then I know that this condition is never going to be true, right? So this will never be true, right? So I'm never going to concatenate anything to A intersect the empty set. So that means that at the end, when I go to say return A intersect the empty set, then I'm actually just going to return the empty set, right? And so this is going to equal the empty set. Okay. The next set operation is the set complement. So if the complement can only really exist when you have a universal set, because the complement of A, which is written A bar, is just the set of elements X that are not in A, but that are in the universe, right? So it can't be anything, right? X can't be like the string cat if you're dealing with integers, right? So so the complement is everything not in A, but I would add, but still in the universe, right? Okay. So for example, in this first question here, when I'm asking for the set complement of 1, 2, 3, this question is actually ill-defined, right? It's ill-defined, meaning that there isn't enough information to answer this question because I have no indication of the universal set, right? So is it the natural numbers, the the integers, the real numbers, right? So my answer changes depending on what the universal set is. And so here, if I ask the same question, but now my universal set is the integers from 1 to 10, then I can write down my complement as all of the integers from 1 to 10 that aren't 1, 2, 3, right? So then that's 4, 5, and so on until 10. And this is a nice question that I'll let you answer yourself. What is the complement of the empty set? What's the complement of the universal set? Okay, the next set operation is the set difference. So the difference of a set A and B is defined as A different B. So A different B is the set of elements X, where X is in A and X is not in B. So if I look again at my Venn diagram, if I have my set A and my set B, it's everything in A. So let's say everything in A, right? This is everything in A, but then everything in A not in B. So then I know that this is also in B. And so what my what my difference is going to be is just these guys here, right? So this is my difference. So this is A different B. Okay, so we look at example 1 here, and I have A is the set 1, 2, 3, 4, 5. B is the set 2, 5, 6, 7. Then what is A different B? So it's all my elements X, or X and A. So for which X is also not in B. So 1 is an A, but it's not in B, so that's good. 2 is an A, but it is in B, so that's no good, right? 3 is an A, but it's not in B, so I can add it. 4 is an A and not in B, so I can also add it. 5 is an A, but it's also in B. And so I can't add that, and so I can close my set difference. I'll leave B different A for you. Let's see, what's interesting here? Yes, okay. So this question is nice, right? So if I have the power set of the empty set, right? So recall the power set of the empty set, that's just the set containing the empty set, right? And then if I have the power set containing the empty set, which is the set containing the empty set, different the empty set, right? What will that give you? Okay, so you might be tempted, right? You might be tempted to say, oh, well, let me just cancel these empty sets. And so I just get this guy. Well, that would be incorrect, right? Because here it's kind of just a trick question based on how I'm representing the empty sets. So if I were to rewrite the empty set here as just the set containing nothing, right? Then remember what you're doing in the difference is you're saying everything in here that's not in here, right? But by definition of the empty set, there isn't anything in the empty set, right? And so when you take a set and you difference it, or you remove all the elements in that set that are also in the empty set, you're not removing anything, right? So not removing anything, right? And so this then becomes the same set. And so in general, if I have a set A different a set, the empty set, then this is always going to give me my set A. Okay, and lastly, this is actually an important property that A different B can also be rewritten. So you can just rewrite this as two sequences of operations. So remember, it's everything not in B, right? So everything not in B, I know, is the set complement of B. So everything not in B, that's also in A, right? So that's also in A. I just intersect everything not in B with what's in A. And so these two sets are going to be equivalent. Okay, great. And now the last set operation is the cross product. This is going to be an operation that's going to come up again and again when you talk about languages and machines. So the cross product of a set A and B is defined as a set of tuples, right? A set of tuples which are denoted by brackets rather than curly braces, where the first element, right? So the first element in the tuple is in A, and the second element of that tuple is in B. So you'll notice that in tuples, tuples are sequence based. So meaning that the order matters, right? So in a tuple, A comma B is not going to be the same as B comma A, right? So that's different, of course, than in sets where A comma B is the same as B comma A. So you can also think of tuples as like um, a more abstract way of representing a string. So let's say I have the string cat, then this is kind of like saying the tuple c comma a comma t, right? Because um, it matters if you have repetition, right? So it matters the string or the tuple cat isn't the same as the string or the tuple, let's say like kata. And if you switch the order of the letters, then this also changes the string or the tuple. Okay, so how does this actually work in practice? So if you have A cross B, right, you can also think of this as kind of like a for loop operation, as kind of iterating through A, right? So for A and A, and then for B and B, you append A comma B to A cross B, right? And let's say you start with A cross B being empty, and then you return A cross B, right? So that's kind of how you would write this programmatically, right? And so if we look at this example here, where we have A cross B, well, A cross B is going to be, you take the 1 here and you join it with all the other elements in B, right? So you have 1, 5, and then 1, 6. And then for the second element, you have 2, 5, and then 2, 6. And for the last element, you have 3, 5, and 3, 6. Okay, so I'll leave the last, I'll leave the last two exercises for you. Okay, they're good to think about in terms of cardinality and also what it means to do the cross product with empty sets. Okay, and as a review, I suggest that you pause the video at this point and go through these operations or exercises on your own, and we'll look at them. Um, so feel free to like pause the video, and then once you're done, we'll look at them together. Okay. So, okay, I'm assuming that you've come back after trying these exercises. So let's go through them together. So this is my universal set, and these are my two sets, right? So what do the following operations yield? So I have A union B. Well, A union B is anything in A or anything in B, right? So anything in A is 7, 8, 9, and then anything in B is 4, 9, 10. I don't need this extra 9, right? So then my set is just 7, 8, 9 for, let's say, comma 10. What about the intersection? Well, the intersection is any element that's both in A and B. And so we just saw that that's actually just going to be 9, right? Because 9 is the only element that's in A and in B. Okay, so then A intersect B is 9. What's the difference? What's A different B? So A different B is anything in A, which is not in B. So 7 is in A and not in B. 8 is in A and not in B, but 9 is in A and it's in B, so I'll cross that off. And so the intersection is just 7 and 8. Okay, let's see here. The complement of A intersect B. So you could have done this in, say, two different ways. You could have first computed the complement of A as the universe minus A, and then taken that result and intersected with B. That's kind of arduous, right? The other thing you could do is just notice that set intersection is commutative, meaning that A intersect B is the same as B intersect A. So A complement intersect B is the same as B intersect A complement. And so I know that that's just B different A, right, from some previous slides ago. So then B different A, sorry, I said B intersect A. This is B different A. So B different A is everything in B that's not in A. And so that we know is 4 and 9 because, sorry, 4 and 10 because 9 is in B and in A, right? So then the result here is going to be 4 and 10. Okay, next, the cross product. So I have A and I want to cross that with 1, 2. So it's the same operation as before, right? You have your double for loop. You take every element in A and you pair it with every element in the set on the right of the cross product operation. So I have 7, 1, 7, 2, then I have 8, 1, 8, 2, and then I have 9, 1, 9, 2. Okay, the last three were actually kind of tricky questions where there seemed to have been like a really complicated operation to do, but actually if you just kind of reasoned about what you were intersecting or cross-producting with, then the answer becomes obvious very quickly. So if I have some set and I intersected with the empty set, there's nothing that's both in A cross B and in the empty set by definition of the empty set, right? And so the result is that I don't have anything to return. I just have an empty set to return. The next thing is if I have some set here and I take the union with the universal set, well, if I have anything here and I have the universal set on the outside, if I do the union, then what I'm going to return is the whole thing, right? I'm going to return the universe. And so the result is going to be the universe. Okay, for H, I have, okay, so this kind of answers the previous question in this previous slide. If I have U, or actually, let's say if I have like any set A, and I cross product it with the empty set, what happens? Well, again, you can think of it as in this kind of double for loop notation. So I have 4A and A, and then 4X in the empty set, append A comma X to A cross the empty set, right? If I say that A cross the empty set starts as the set containing nothing, well, this, right, this for loop never executes. Why? Because there is nothing, so there does not exist, right? This is if you remember from discrete structures or discrete math, this is the notation for there does not exist, because there does not exist an element X in the empty set, right? So the for loop never executes, and so what you end up returning is just what you initially assigned the empty set, which was just the empty set. Or sorry, what you initially assigned A cross the empty set, which was the empty set. And so this is going to be the empty set. Okay, and finally, for this exercise, this one was maybe a bit trickier. So I had some set, let's just call this X for now, intersect the universe. So if I have some set, say X, and I have the universe, the intersection is anything in X and in U. But because U is the universe, that's actually just going to be anything in X, right? So X intersect the universe is X, right? So now what I need to compute is X. X is A complement union the empty set complement. Okay, so what's the empty set complement? Well, it's everything not in the empty set, right? So where can I put this? So the empty set complement is the universe minus the empty set, right? So it's everything in the universe that's not in the empty set, but nothing is in the empty set, right? So that means that the result is the universe. So then I have A complement union the universe. Wow, this is annoying. Okay, A complement union the universe. But then I just saw before that if you take anything and you union it with the universe, you get back the universe, right? And so the result of this is just the universe. Okay, so that does it for set operations. This is just some extra set properties that you're free to look at. In the next in the next video, we'll do a review of graph theory, and in the one after that, we're actually going to be proving one of these theorems. So this is, if you remember from discrete math, De Morgan's law, where if you take the complement of the intersection, you get the union of the complements. But you can prove that this is true using a certain technique. And so down the line, what we're going to look at is proof techniques. Okay, so that's it for this video though. So see you in the next one.